Okay, so let's get started. Today we're going to talk about the attention mechanisms in RNNs. Just as a recap, last lecture we talked about the problems of one-hot encoding, and then we saw word embeddings as a way of solving those problems. And we talked about two particular models, the word2vec and glove. So for today, we're going to see the idea of attention in RNNs. And to talk about that, we need to motivate this discussion with machine translation, because that's where the idea of attention started. So machine translation is this problem of giving sentence pairs X, Y, where X has TX tokens. So, and we're going to see X as our input sentence in one language. So you see there that there is TX elements in this sequence X. And we want to predict an output sequence Y that might have a different length, for example, TY. And that output should be the translation of the sequence X, okay? So this table is one small example of data set from Portuguese to English. So here we have 4 sentences, Olá, como vai? Hello, how are you in English? And then o livro está em cima da mesa, the book's on the table. And there is a tricky one here, because the last two ones, they are actually the same sentence translated in different ways. So actually, they are different sentences translated in the same way, in this case. So, Lucas irá viajar ao Rio em dezembro could be translated to Lucas is traveling to Rio in December. And then you could have another sentence, em dezembro, comma, Lucas irá viajar ao Rio, which could be translated the same way. Okay. And you could have the opposite, right? You could have the same sentence in Portuguese with 2 different English translations. And that's common in machine translation data sets, okay? Because that's actually possible, right? There is many different translations for a given sentence. So this is just to illustrate the problem. We already talked about this a little bit, and we can use these sec-to-sec models to solve these problems, okay? So in the sec-to-sec models, we have an encoder and a decoder, and the encoder processes the sequence element by element, producing a hidden state at the end, edge TX, right? Which is used as a condition, we say, is a condition to the decoder model. Because the decoder now has to produce an output sequence of length TY, but starting its first edge 1 context with the edge TX context from the encoder, or the last hidden state of the encoder goes into the first hidden state of the decoder. And keep in mind that these 2 networks are independent from each other. So they have their own weight matrices, okay? So we have 2 weight matrices for the encoder and 3 here for the decoder, because the encoder doesn't have the output layer. So it only has 2. So we can think about this edge TX vector as a kind of a vector representation of the entire sequence, or the input sequence. Okay, so it's a way of compress that sequence. Okay. And that's the model we typically use for machine translation. These days, we use the transformer architecture, as you'll start seeing next week. And the transformer architecture also has this structure of encoder and decoder, okay? Because it was thought or initially designed for this task of translation, so it also follows this idea of encoder-decoder. But the encoder and the decoder of the transformers, they just do different computations than this, okay? That are slightly more complicated. But any questions here? Okay, I'm going to go slowly. So I said the word decoding a couple of times. What do I mean by decoding? So decoding is a process, it's a problem actually, of finding the most likely translation. As we already talked about, a given sentence might have different translations. And I want to find the one that is more likely among all of them. Okay? So we define this as a decoding problem. So formally or mathematically, we want to find a sequence y1, right, dot, 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 yty, that maximizes the conditional probability, and then p of y1, dot, 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 yty, given that x occurred, where x is our input sequence. Okay, so that's the formulation in terms of probability that we want to do. So let's think about that input sequence x. Lucas irá viajar ao Rio em dezembro. Okay? So we could have the following translation. Lucas is traveling to Rio in December. We could have this one. Lucas is going to be traveling to Rio. It's missing a 2 there in December. Or in December, Lucas will travel to Rio. And Lucas is going to a conference in Rio, maybe just by chance. Okay? Anyone could argue that the first 3 ones are correct translations of the input sequence x. Most likely, more people would agree that the very first one there is the best translation among the 4 of them, even though it's debatable, but most people would say the first one is the best because it's more concise. The second one is correct, but it's more verbose, right? You have that is going to in the middle, that is unnecessary. So, but it's still valid English and it's correct grammatically. It's just not as ideal as the first one. The third one is also right, not the type of, it's changing the structure a little bit, so maybe it's not what we want. And the fourth one is a little bit off, right? It's not, it threw like this conference in the middle that wasn't there in the original sentence. But anyway, those are possible strings or sequence of words that could be decoded by our model. Okay? Just the way it works. Okay? So formally, we want to optimize that objective function. We want the sequence y1 dot 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 yty that maximizes that probability. And there is 2 common ways of solving this problem. We call these decoding algorithms. So we typically use greedy search or beam search. So you might have seen these 2 algorithms already in other contexts, in computer science or AI. So greedy search is the simplest algorithm we can use, and it works by selecting the most likely word at each decoding step. So here is just an arbitrary example, right? Lucas irá viajar ao Rio em dezembro. We start our hidden state with edge 0 equals to 0. We pass that through the encoder RNN that gives us the last hidden state of the input sequence, or the encoder, and that's our condition. That's our compression of that input sequence. These are just arbitrary numbers. Don't worry about them, okay? It's just to illustrate. So edge 1 is going to produce, is going to actually be using the output layer that is in blue, right? And the output layer produces a probability distribution over the entire vocabulary. So if you look at those numbers in blue, they should be summing up to 1. Okay? So what the greedy search does is pretty much, that's weird. So this is wrong. So this should be 0.3 here. So the greedy search, we're going to pick the word that maximizes, that has the highest probability among all of the words in the vocabulary, which in this case would be Lucas. Okay? I'm assuming the vocabulary has only 5 words there, but it would be, that vector would be a 10,000 dimension vector. Okay. And then you now, what we do is we send that word that we sampled, Lucas, as input to our next step. We update the hidden state, so these numbers should be different, right? These numbers here should be slightly different. I'm going to just guess a bunch of numbers here, minus 1.2, or maybe let's just minus 1.0, 0.3, and then 0.2. Okay. Yeah, this is going to be different, but anyways. So I'm going to do the same thing again now. I just pick the word is because it has 0.9 probability, which is the highest among all of them in that time step. And then I do that again. Now I select the word going with 0.7 probability because it's the highest among those in that step. So I keep doing that until I find the end of sentence token. And this works okay, but it has a problem. Since in this example, right, Lucas is going is more likely than Lucas is traveling in the English language, because is going is a very common expression to have in English, right? So most likely in that scenario, Lucas is the language model or the machine translation algorithm here or model, or the greedy search in this case, would pick going instead of traveling. Okay? Just because is going is more likely, Lucas is going is more likely than Lucas is traveling. So it will end up producing a worse translation, like Lucas is going to be traveling to Rio in December, instead of the one we would expect, which would be Lucas is traveling to Rio in December. Okay? And this is just because we are being greedy at each time step. We are not actually evaluating every possibility of sentence. Let me show you this with a visualization. So I'm not showing all the possible combinations of sentences that we could have in English, starting with Lucas, but consider this diagram starting with the word Lucas. Imagine that I had 3 possible words to pick after Lucas: was, is, and will, with probability 0.32, 0.4, 0.28. Okay? And then after Lucas is, I could get Lucas is visiting, Lucas is going, and Lucas is traveling, right? And those are the probabilities associated with those subsequences. Okay? So if you look at what greedy search will do, it will pick at each step, it will pick the most likely word, which in this case, you would start with Lucas, and then you would pick is, because is has 0.4 probability, which is greater than 0.32 and 0.28. And now we are in this Lucas is subsequence. We have the options visiting, traveling, and going. And going has the highest probability with 0.5. So I'm going to pick going. And then I have now the options to, and with. And the greedy search will pick to, because it's the most likely one in this subsequence Lucas is going. And if you compute now the probability of the whole sequence, which is 0.4 times 0.5 times 0.6, that will give you 0.12. Okay? But if you investigate other options, other combinations of words, you would see that the optimal solution is down here. Right? Lucas is traveling to, sorry, this should be Lucas is traveling to, with probability 0.144. Okay? So by being greedy, you can miss branches of the search tree that have a higher probability, because ideally what we would need to do is actually to simulate all the possible sentences and compute the probability of the whole sentence and pick the one that maximizes that value. Okay? So you can't, if you be greedy, if you just go greedy here, you're gonna be suboptimal. Okay. So one solution to that is using beam search, which is a local search algorithm, so it's not guaranteed to provide you the optimal solution, but it does much better than greedy search. And it's on the other end of the spectrum. We can't run breadth-first search or depth-first search here because the vocabulary is just too large. We can't explore all the possible combinations of words because it's just too many words and too many combinations. So we're going to approximate a solution using beam search, and that is a local search algorithm. And what it does is it simply keeps B solutions at each decoding step. Okay? Instead of keeping just one, we're going to keep the top B solutions in a structure that we call a beam. That's why the algorithm is called beam search. So we start with the vocabulary. Now this is our 10K vocabulary. Starts with the word A, and the last word is Zulu. So the first thing we do is we get the top B most likely words to form our first beam. And our first beam here there has December, In, and Lucas, just because they have the highest likelihood among the other ones to start a sentence. Okay. So then what we do is now we're going to evaluate all possibilities of sentences starting with December, and then starting with In, and then starting with Lucas. So we're going to evaluate B times 10K solutions now. Now, just by looking at the figure, we are using a B equal to 3 here. Our beam has 3 solutions, December, In, and Lucas. So I'm going to evaluate all the possible, 30,000 possible next solutions. First start with December, then In, then Lucas. Okay? I couldn't draw all the arrows there or the edges, sorry, because it would be too much. But when you see this like dashed lines there, it's just to show that you actually have to evaluate for a given word. You look at all the vocabulary and check the probabilities of these sequences. But note that I'm only doing this for the top 3 words, not for all the words, okay? Which makes the whole search much more practical. It's not an exact search, but it does a better job than greedy search. But then what you do is just to get the top B most likely sequences again. And now, for instance, assume that In December is one of the top 3 likely solutions, and then Lucas is also a top likely sequence, and then Lucas will. Okay, so these 3 now are going to form my beam. So now my beam has In December, Lucas is, and Lucas will. So now I just repeat steps 2 and 3 in a loop. Okay. So now I have these 3 solutions. So I'm going to evaluate for In December, I'm going to evaluate all possible words after In December, and then after Lucas is, I'm going to evaluate all possible words, and then after Lucas will, all possible words. Okay. Does this make sense? And here I'm going to evaluate B times 10K solutions as well. Yeah, and just to keep going now. Oh, something that is important to highlight is see how the way the algorithm works. In the first iteration, I actually threw away the branch starting with December because it was just less likely than all these other 2 here. Okay. And that can happen. You can kill some branches as the algorithm is developing, is actually unfolding. Okay. It happened here again, right? Lucas will was thrown away because just these 2 sequences here, Lucas is going and Lucas is traveling, is just more likely than any other sequence start with Lucas will. Okay? So this can happen. And one good thing about beam search, also in the context of machine learning, is that you can actually do this vectorized. So it's much faster. You don't need to evaluate these 30,000 solutions in a loop. You can actually do this with vector operations. Okay. But regardless of the decoding strategy, and this is the key motivation for attention, it's really difficult for these sec-to-sec models to translate long sequences because they have to compress the entire input sequence X in a hidden state only, right? So this 3-dimensional vector here is compressing the whole sequence. So if I had a very long input sequence, like Lucas is traveling to Rio in December to attend a conference about music and artificial intelligence that will be hosted at the Federal University of Rio de Janeiro, he will go with one of his students, right? If I had such a very large sentence like this vector with only 3 numbers would have to compress that whole sequence, and that makes it very hard for the decoder to be able to decode a good translation, right? Which would be that, Lucas irá viajar ao Rio em dezembro, blah, 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 right? So basically our hidden state in the middle there is a bottleneck to our model. And if you think about this, right, let's look at that word ele, which is a pronoun, right? To get that pronoun correctly, ele, which refers to Lucas, it has to carry, so somehow this hidden vector here has to carry the information of Lucas all the way from the beginning to the sentence to here, right? And it's hard to do that because we are processing each element one at a time. So every time we update our hidden state, we have the risk of forgetting what we saw before. So we are always bringing new information and blending with previous information. Okay? So it's very hard for the decoder to produce translations for these long sequences because the way the encoder works, right? It keeps bringing new information, so it's very likely the very first ones, they'll be forgotten, okay? Because you don't have enough expressivity in your vector. You don't have enough dimensions to do that. And even if you increase the size of your hidden vector, it still becomes very hard. Because there's just too many things to keep track of to produce a good translation, okay? That's just one example, right? The subject of the sentence, but so the subject is going to somewhere, is going to be at some other place, so you have to remember all these things to actually be able to produce good translations. And that's the problem you're going to try to solve with attention, okay? And that's the core of this lecture. Okay, we have about 40 minutes to understand what an attention is, and this is the first idea of attention. It was proposed for RNNs. Okay, so when you see this term, and which is very popular in deep learning these days, attention has been used in computer vision. It started in natural language processing, but then people are using computer vision in other fields as well. But it all started here in this paper, 2014. Okay, Neuro-Machine Translation by Jointly Learning to Align and Translate. So it was also conceived in the context of translation. So in this slide, I actually have exactly the same structure of sec-to-sec model. We're going to start with an encoder, a decoder. Here I'm just showing the very first time step of the decoder, because as you will see, the attention part will take some space on the slide, but all the other time steps are exactly the same. So I'm just doing one time step for us to understand how attention is computed. But we start with the same structure. One key difference that I'm doing here is I'm calling now the hidden states of the decoder with the letter S, just to separate these two things, okay? I'm just changing the name of the state, okay? So whenever edge comes to the decoder, it becomes S, okay? And the very first version of that vector, S0, is a little bit out. I put it out of the decoder because I think it makes more sense in this case now, okay? So S0 is equal to edge 5, okay? And S1, we're going to produce S1 from S0 now. And here is how it's done, okay? So bear with me, this is not a very intuitive idea in the beginning, but the more you see it, the more it makes sense, okay? And turns out it's perhaps one of the most important ideas in deep learning these days, okay? Because it enabled the transformers, which enabled a bunch of different things like ChatGPT and so on, okay? So before we had attention, we would process this whole sequence and get an edge tx, which was 1, 2, 3, 4, 5, an edge 5. And then we would use this edge 5 to produce a translation step by step. With attention, I'm going to still produce my outputs step by step. But what I want to do is connect each word from the input to every decoding step in my decoder. Okay, so I want to make my model, I want to allow my model to, before deciding the next word, to look at the whole sentence every time. So it doesn't have to just memorize the whole thing with one vector, because it will now have access to every hidden state before decoding and finding a word, or deciding which word to use. So I want to decide a word that comes after SOS, which would be a word y hat 1. So to decide the word y hat 1, I want to look at all my words. Okay? And then I also have access to this, to SOS. And I want to now decide which one is more the most likely word here, looking at all of the other ones. So I now have the context of the whole sentence. Every time step, I'm going to have that. Okay? So what we want to achieve at the end is to somehow have a alpha weight here for each of these words. Let's call them alpha 1, 1, alpha 1, 2, alpha 1, 3, alpha 1, 4, and alpha 1, 5. So those are weights. Okay? And what we are doing right now is computing these weights. So I'm going to multiply that hidden state by a weight, and then I'm going to do a weighted sum of all these things, and I'm going to call that a context vector C1. So C1 is going to be something like this. I from 1 to 5, alpha, this is T. Let's call this T prime. 1 to T prime, alpha, edge. And I want this weights here to sum up to 1. Okay? So let me show you what we wanted. We wanted something like this. Edge 1, let's make up some numbers here. This could be 0, 0, 1, 0, 1, 2. And then this could be minus 1, 0, 0, 1. Dot, dot, dot. Edge 5 could be 1, 1, 2. I don't know. So alpha 1, 1 is going to be multiplied by this vector. Alpha 1, 2 is going to be multiplied by this one, all the way down to alpha 1, 5. What I'm saying is that these values have to sum up to 1. So this could be 0.1, 0.5 maybe, and then imagine all these ones are zeros, so we have 0.4 here. 0.5 is, yeah, 0.6. Okay. And we're going to sum these results to produce what we call a context vector. And we're going to now decide the next word based on this context vector. The challenge here is how to make up these weights. And you can think about these alpha weights is, for example, for this word, if we know, let's say, we know that the answer here, y, is Lucas. Okay? The model doesn't know it, right? But we know. So just we have it here as a reference. So you can think about this alpha weight as how much the model should pay attention to the word Lucas when decoding this word here. Since this is the very first word of our sentence, and by looking at many examples, we normally know that the first word is a name, so the alpha value here for Lucas should be very high. So this should be 0.9 perhaps, and this 0.05, and this 0.05. So then look how these are going to be close to 0 now, and I'm going to just have left the edge 1. So the model will have more attention to the vector edge 1. Okay, so that's what we want. It's just to produce some weights that what we think about as an attention is these weights. So how much attention, how much weight I want to put in one word. Okay? Sorry about my bad hand drawing, but that's hopefully the idea is there. So to produce the alpha weights, first thing we do is produce these E factors. These fully connected layers are defined as follows, right? E1 T prime. T prime here is the time steps of the encoder, sorry, right? And so I'm going to just have 2 weight matrices for each of these fully connected layers, and I'm going to produce with a tonnage a value E for each of these fully connected layers. Okay? And then, because we want to normalize the weights to make them sum to 1, we pass them through a softmax layer. That's it, right? There's nothing really more complicated than that. So now my alphas are there. And they sum up to 1 because of the softmax. Those are also scalars, right? They're not vectors. So here's perhaps the tricky part, is we multiplied those alpha by the hidden vectors. Okay? So now we just have to sum them. And that gives us the context vector C. And that whole thing there that you see, that whole block you see is the attention block. Okay? And as a circuit, it looks kind of complicated, but all it's doing is that equation up there. C1 equals to sum from 1 to 5, alpha 1 T prime, edge T prime. It's just a weighted sum. Just the way you compute the alphas, the weights, is through this fully connected layer. Okay? So we let the model learn the weights for us, these alphas. So as you train these models, the model will give more attention to different words depending on how the examples are created. And now, let's just erase this and do it again, right? Just so we make sure we understand what's going on. Now, before I do that, let me just show how this is connected. So, when I say attention, I'm talking about that equation, okay? And this is one type of attention, and it was the first one. Nowadays, there's many other types of attention that just implement this idea of a weighted sum in a different way. Okay? And the transformers, they do that slightly different as well. You'll see that the diagram is going to look very similar, but they don't use, for example, the transformer doesn't use these fully connected layers. It uses a different thing. Actually simpler, it uses a dot product only. So, and you'll see that. So when you read the papers, you'll see that one attention is called additive attention. The other one is called scale dot product attention. So you'll see that there's many different types of attention. And when they say that these kind of attentions, they are talking about different ways of computing that context vector. But attention is just this weighted sum at the end of the day. So now that you produce your context vector, the only thing that changes now is that you actually plug that to form your next hidden state. And then you produce your you produce your output. So now the decoder has access to the context vector, to the previous hidden state, and also to the input at that time step. And we still pass over the previous output as an input to the second time step. So the next thing is just the same, exactly the same thing. So yeah, that's what I wanted to do right now. So let's do it again. So we have Lucas. I'm going to try to do it slowly and with a better handwriting. Lucas irá viajar em dezembro. So here we have edge 5. And let's assume, so we already have this step S0 done. So, and then we are also already did S1. We just did that on the slide. So let's just copy this. This is SOS here. And this is going to produce Lucas. Okay? So this word is connected as an input to S2. Okay, S2. So now I have to guess the second word. And I have to produce the context C2. So we already computed C1 by looking at all these words. And this one went here. So now we have to produce C2. Let me put some more space here. S2. So this one goes here. This one goes here. And then, yeah, and then I'm going to guess a second word. So I'm going to erase these connections. And this is, just so you remember, edge 1, edge 2, edge 3, edge 4, and edge 5. This becomes S0, yeah. So now we're going to compute C2. And we have the alphas again. But now I have alpha 2-1, alpha 2-2, alpha 2-3, alpha 2-4, sorry, and alpha 2-5. Looking at the slide, I multiply this alpha by this hidden vector, this alpha by this hidden vector, this one by this, sum all of them, and that's my C2. Then C2 goes to S2, then I guess the word. So I already produced S1, this is one time step, done, right? Produced S1, so the flow is from left to right, right? So I start here, I go up here, let me use a different color maybe. I have S0, and then I compute C1, then I pass this over here, produce S1, then I guess the word, right? Then now I pass this over here, produce C2, okay? Put this back here, pass this one here, copy this over here, and then I guess the word. So what is important here is at each time step, I have to recompute those alphas because I'm actually at a different time step of the decoding. So the attention I should pay when I'm in the beginning of the sentence is different than attention I should pay at the end of the sentence. Right? That's the idea here. The alphas should be different in the beginning. For example, in the beginning, there's way more chance to put a name in the beginning of the sentence than at the end. At the end, I should be probably looking for here a month or something, right? So every time step, what I'm trying to, the task of decoding is slightly different. And so the words I should pay more or less attention are going to change. So in the beginning of the translation, I'm probably going to look more over here. But as I move towards the end of my translation, I should probably give more attention to the end. As we do when we're translating, right? First of all, we don't memorize the whole thing. If I give you a sentence to translate, you won't memorize the whole sentence and then try to do word by word. You pick the words one by one, but every time you're confused, you're going to look back and say, okay, maybe this is the word, right? So you always go back and forth when you're translating yourself, like as any language, right? If you're translating from English to Portuguese. You always go back and say, oh, Lucas is, so it's traveling, so viajando, so now para, so, right? And then you always have this attention. You look back at some parts of the sentence as you need. So the idea is to kind of simulate that process. At every time step, you have the chance of looking to the whole sentence again. Okay? If you want to remember something, it's just it's just basically that. It's that equation. It's just weighted sum, and you need a way to compute alphas. You can compute alphas in different ways, and this is one way. And that's it. And then you decode normally. Okay. And it's tricky because this is attention in RNNs. As you will see, attention in transformers, they follow the same principle, but they won't have this recurrency anymore. You wouldn't have like step 1 and step 2 and step 3 and step 4, because the transformer does all of them at once. And that's one of the big contributions of the transformer, is that it can process sequences without a for loop over time. So it kind of unrolls this for loop beforehand, and then you work in a window. So because of that, the transformer cannot process infinite sequences. It has to work with fixed length sequences, but it's much faster, much easier to train, and you can make it bigger because of that. And I want to stop right now. I don't know what time is it. Yeah, it's actually about time. Because I think this idea is not very intuitive, as probably you're already like feeling it. But the more I think about it, I'll try to give you some examples. Maybe I'll see if I can find a nice implementation of this, of the original attention in RNNs, so you can probably look at what's going on and maybe play with the code, and maybe that actually makes it easier for you to understand. But it's just that equation up there, guys. Don't worry too much, okay? Okay, so next lecture, we're going to talk about the transformer architecture. And yeah, it might be one of the most important lectures of the course. So. Thank you very much.